share the screen.
Just 1 second. Yeah. Are you able to see my screen?
Yes, ma'am.
Yeah. Okay. Good evening, everyone.
Good evening, ma'am.
Can I start, Swati?
Yes, ma'am. Before that, can I just tell the students?
Yeah.
So, hello, good evening, everyone. So, today the sessions will be taken by the Usha ma'am. So, you just like the same drill only, that you can't ask any general doubts or any questions that are related to the assignments or anything. You will just ask the concept that she is teaching you. Okay. And please maintain silence and decorum and only ask when you have doubts. Okay. Is that clear?
Yes, ma'am. Yes, ma'am.
Okay.
Yeah.
Right.
Okay, ma'am.
Thank you. So good evening, everyone. So the way we'll proceed with the session for the benefit of everybody. This is a session where we are going to have a revision of the concepts on random variables and probability distributions. In particular, we are going to look at discrete and continuous distributions along with the random variables. Okay. So as Swati mentioned, I will give time after every concept or every subsection, some time for discussion, during which all of you can ask questions. But I think let's avoid interrupting when the particular concept is being discussed, and we will not be discussing anything that is specific to a particular assignment. You have your other sessions where that can be done. Okay, so let's move forward. So what can you expect today? You can expect today the following. I hope my screen is visible. Yeah. So today's session, what you can expect is you're not able to see my screen.
No, ma'am.
Ma'am, it's looking totally grey.
1 second. Are you able to see now? Not yet?
Yes, ma'am. Now
Yes, ma'am.
Okay. So what we are going to do today is we will start with, so I have just modularized it into 3 sections. In the first section, we'll look at random variables. In the second section, we'll look at some discrete distributions. And in the third section, we'll look at continuous distributions. This is the plan or the agenda for today. Now, why a random variable? So if you all recall, when we were talking about probability and probability random experiment, the building block for probability was that of a random experiment. So let's go back and understand what we did there is first we defined what was a random experiment. And then from a random experiment, we defined what was the sample space of a random experiment. Okay. Now, when a probability experiment is performed, many a time you might not be just interested in knowing what is the outcome, but you might want to know something about a numerical quantity that is actually associated with that outcome. What do we mean by that? For example, if I toss a coin twice, I'm going to get a sample space which is HH, HT, TH, and TT. Right? Is my screen visible? Are you all able to see what I'm writing?
Yes, ma'am.
Yeah.
Yes, ma'am.
Now, instead of these outcomes, which are two heads, one head, and one tail, I might want to map these outcomes to a number, which is I could count the number of heads, which is 2, which is 1 here, which is 1 here, and which is 0 here. In other words, what we are trying to say is I'm mapping every outcome of the sample space to a numerical quantity. I repeat, I map every outcome of the sample space to a numerical quantity. I am going to first look at discrete and then we'll go into continuous random variable. So let's look at another example where I am tossing or rolling a dice twice. So when I'm rolling a dice twice, all of us know this is the sample space. Agreed? All of us know that this is the sample space of rolling the dice twice. Is it clear? So are you all able to see the sample space? I have 36 outcomes of this sample space. Is the sample space visible?
Yes, ma'am.
Right. Now, of these outcomes, I'm interested in a random variable, which is the sum of these outcomes. So what are the values this random variable will take? If I'm going to define a random variable, which is the sum of the outcome, what is the value that is associated with 1, 1? It is 2. With 1, 2, it is 3. 1, 3, it is 4. With 1, 6, it is 7. Again, 2, 5, it is 7. With 6, 6, it is 12. So if I am calling a random variable x to be nothing but the sum of the outcomes. So I'm associating a numerical value with each of these outcomes. Okay. And I can map each of these outcomes to this random variable. I can also define another thing, which is the maximum of these outcomes. For example, if it is the same outcome, I'll take it as the same. So what is y for 1, 1? It would be just 1. For 1, 2, it is going to be 2. 1, 3, it would be 3. 1, 6, it would be 6. Just as I define maximum of outcomes, I can also define the minimum of outcome. Again, for 1, 1, it would be 1. 1, 2 is going to be 1. 1, 3 is going to be 1. So for all these outcomes, the value z would take would be 1. For all these outcomes, the value z would take would be 2. If I'm defining maximum, you know that for all these outcomes, okay, it is going to be 6. For all of this, it is going to be 5. For all of this, it is going to be 4. So this is what we start with by I have a random experiment, and on this random experiment, I'm mapping every outcome to a value. Any questions still here? Is it clear?
Yes, ma'am.
Yeah, right. So now let's go back and formalize whatever we have discussed in the following way. So x is denoting the sum of the two outcomes and y is denoting the lesser of the two outcomes. So you can see that for each of the outcome, I have what is the value x takes and what is the value y takes. Okay. So x is taking value 2 to 12 and y is taking value 1 to 6. Okay. So I repeat, x is taking value 2, 3, 4, 5, 6 up to 12 and y is taking the value 1, 2, 3, 4, 5 and 6. So what is it that we are expecting from this? Okay, I have the outcomes of my sample experiment and I have actually looked at what is the value it is taking. So the natural question that I want to ask here is, what is the probability with which x takes the value 2 or probability with which y takes the value 1? So if I look at x taking the value 2, I see that there is only one outcome with where x takes the value 2. On the other hand, if I'm looking at x taking the value 3, I have this outcome and I have this outcome. So what I can do is, associated with every value x is taking, where I'm defining x to be the sum of the rows, I can map what is the relevant event to the value of the random variable. Till here, is it clear? Yeah?
Yes, ma'am.
Yes, ma'am.
Right? So I have x, which is a random variable, which is taking the values 2 to 12, and I'm mapping what is the relevant event for every value. Similarly, I can look at y also, and you can see that y takes the value 1, 2, 3, 4, 5, 6. For each of the values y is taking, I'm mapping what are the relevant events. So once I map the relevant events, I go back to my basics of probability. I know how to find out what is the probability of an event. For example, I know how to find out the probability of this event which I have mapped with x equal to 2. Why? How do I know this probability? Again, I know that the sample space which I have here, has equally likely elements. So what is the probability of this event 1, 1? Anyone? What would be the probability of this event 1, 1?
1 by 36.
1 by
1
36.
by 36. What is the probability of this event?
2 by 36.
2 by 36. So I can in fact write this as probability of x equal to 2 is nothing but the probability of that relevant event. Probability x equal to 3 is the probability of that relevant event, and I get probability x equal to 12. Take a minute and write down the probabilities for y, where y is the lesser of the two values. I give you all a minute. Take your notebooks and write down what is the probability of y. What are the values y is taking? And what is the probability of y equal to 1, y equal to 2, up to y equal to 6? Okay. So y is the lesser of these two values. So if you look at what is the value this y is taking, you all would have got something of this kind, where y takes the value 1, 2, 3, 4, 5, 6, and probability y equal to 1 is nothing but 11 by 36, y equal to 2 is 9 by 36, up to y equal to 6 is 1 by 36. Is it clear till here? So what we have done, we have started again with the sample space. For each element of the sample space, we have mapped the element to a particular value. I have defined here two random variables, x and y. X is the sum of the values and y is the minimum of the values. I can look at absolute difference or difference of the values. I can define as many random variables as I want, but these are the two random variables I've taken. And then I looked at what is the probability with which x takes a particular value and y takes a particular value. This probability with which it takes a particular value is what we call the probability distribution of the random variable. Any questions still here? Is this conceptually clear?
Yes, ma'am.
Right?
Yes, ma'am.
Okay.
Yes, ma'am.
Right. So once I define all of it, I now go back to just define what is a discrete and continuous random variable. Now, suppose I'm tossing a coin till I get the first head. What would be my sample space? If I'm tossing a coin till I get a head, what would be my sample space?
H,
H,
T,
TH,
TTH,
TTH,
TTTH.
TTTH. Okay, and I'm defining a random variable to be the toss at which I'm getting a head. So what are the values this random variable will take?
1, 2,
1,
1, 2,
0, 1,
3,
and 2.
4, so forth. Right? Agreed? And what is the probability with which x equal to 1?
It could be 1.
Probability x equal to 1. If p is the probability of getting a head, what would be probability of x equal to 1?
1 by P.
1 by p? X equal to 1. Probability x
P
equal
by
to 1.
8.
What does
1 by
probability
8.
x equal to 1 mean? It says that I'm getting a head in my first toss. Would you agree? Yeah.
Yes, ma'am.
What is the probability of
Yes,
getting a head in the first toss?
Ma'am, 1 by 2.
1 by 2.
1 by 2, or it is p if p is the probability of getting a head. What is the probability of x equal to 2?
1 by 4.
1 by 4.
Which will be 1 minus p into p. Agreed?
Yeah, ma'am.
Yeah. So you can see that here, what is the difference between the way I have defined my random variable here and the earlier thing? In the earlier way, when I defined this both x and y, they were taking finite values. Nevertheless, they were countable. Whereas here you can see x can take any value, 1, 2, 3, 4. Is the difference clear? Right? So a random variable can take either only a finite number of values or countably infinite values then I call that random variable to be a discrete random variable. Is this concept clear? That is a random variable that can take on a finite number or a countably infinite number. So in a discrete random variable, the key things I need to understand is I can count. So whenever I can count, I tell it is a discrete random variable. Is this clear?
Yes, ma'am.
Yeah. Now, however, when the outcomes of a random experiment are numerical but cannot be counted, that is, it is infinitely divisible. That is, I know that probability x does not take a discrete integer value, but it belongs to an interval. I call that random variable to be a continuous random variable. So the first thing that we need to understand is what is a discrete random variable and what is a continuous random variable. Okay. Now, let's formally define it. A discrete random variable is a random variable that has discrete values. It typically involves counting, whereas a continuous random variable has values that form an interval, and continuous random variables typically involve measuring. I repeat, when you talk about a discrete random variable, it typically involves counting, whereas a continuous random variable typically involves measuring. So let me start by a quick check. When I talk about number of people in a household, do you count or do you measure?
Ma'am, we
Ma'am,
count.
count.
So will it be a discrete random variable or will it be a continuous random variable?
Discrete.
Discrete.
Now I'm talking about temperature of a person.
We measure it.
Continuous. Height of a person.
Continuous.
Weight.
Continuous.
Yours.
Number of accidents that take place in an intersection.
Discrete.
Time taken by a person to write an exam.
Continuous.
Speed of a vehicle.
Continuous.
Number of spelling mistakes in a report.
Discrete.
Number of languages a person can speak.
Discrete.
Okay, so this always, whenever you're presented with any such problems, first understand whether you're counting or you're measuring. If you are counting, it is going to be discrete. If you're measuring, on the other hand, it would be continuous. Is this clear?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
So now let's look at, we have already seen what is a probability distribution. What do I mean by probability distribution? I know that my random variable takes discrete values. Okay. So now let me generalize that to write it as, when I looked at the sum of two random variables, what was the value my x was taking? My x was taking values 2, 3, 4 up to 12. And I am interested in knowing what is the probability x equal to I. So what is the probability x equal to 2? We saw that was 1 by 36. This was also about 1 by 36. This was 2 by 36 and so forth. Right? So in general, if I have a random variable x, which takes values x1, x2, xn, with probability x equal to xi or x1, probability x equal to x2, probability x equal to xn. Okay, these are the probabilities with which random variable takes the values. I can also write this as probability of x1. I can write this as probability of x2. I can write it as probability of xn. Just notational convenience that I am denoting this probability x equal to xi as p of x1, x2, xn. Okay. Some books might refer to it differently, but this is just notational convenience. What I want you to understand is, if I present data to you in this form, that x is taking values x1, x2, xn with respect to probability x equal to x1, probability x equal to x2, and probability x equal to xn. I'm assuming it is taking n values. Then I call this representation as the probability mass function of the random variable. Okay. Now, what are the key characteristics or properties of the probability mass function? The key properties, the first property is probability is always non-negative. This is a This is something that we already know. Okay. So I have the first thing that probability is greater or equal to 0. And the second thing is, since it should take a value 1, the sum of all probabilities, if suppose I have x1, x2, it is infinite, countably infinite, then the sum of all the probabilities should be equal to 1. Now, why is this again important to you? You might have seen problems where you will be asked to verify whether a particular problem is a probability mass function or not. For example, suppose I say x takes values -1, 0, 1 with probability 1 by 4, -1 by 4 and 1. Is it a probability mass function?
No, ma'am.
No, ma'am.
No.
Why not?
Negative.
Negative value.
It is adding to 1, but I have a negative value. On the other hand, if I said 1 by 4, 1 by 4, and I have 1 by 4, then
It's still not. No.
it is still not a probability mass function because it is adding to 3 by 4, whereas it should add to 1. Is it clear? So you have problems where you might have to verify whether a given function is a probability mass function, or for example, let's say x takes the value -1, 0, 1 with probability x equal to -1 is 1 by 4, x equal to 1 is 2 by 4, then what is the probability of x equal to 0?
1 by 4.
1 by
1 by 4.
Okay, so these are the types of questions that you can expect that, and this is directly following from the conceptual understanding of what is a probability mass function and what are the properties of the probability mass function. Now, another thing that is very important to us is to know what is the shape of the distribution. Now, when I want to know what is the shape of the distribution, I know that x takes, so I have x which is taking values x1, x2, say xn, and each one of them is taking it with a particular probability. So I put those probabilities as bars, and a function that resembles this is nothing but plotting probability x equal to xi on the y-axis and xi on the x-axis gives me what is the graph of the probability mass function. And from this graph, I can identify whether a distribution is symmetric or skewed. So whatever you can see on your screen here is a probability. First of all, let's check whether it's a probability mass function. Is it a probability mass function?
Yes, ma'am.
Yes.
Yes.
Right? Because 0.7,
Yes,
0.9, 0.1, it is a, but if you look at the distribution, it is skewed. It is a positive skewed distribution. On the other hand, again, let's check this. Is this a probability mass function?
Yes.
Yes, but you can see again it is skewed. It is a negative skewed function. Okay. On the other hand, if I had a problem which is 0.1, so I had x equal to 1 is 0.1. Okay, and this is 0.3. This is again 0.3. Okay, this is a 0.2 and a 0.2. What would be the shape of the distribution? First of all, is it a probability mass function?
Symmetric.
Symmetric.
So I have 0.1. 0.3, 0.3, and 0.2, you can see it is symmetric. Okay. So the need for us to go in for a graph of a probability mass function is to understand what is the shape of the distribution, and shape of the distribution will give us a lot of insights. The next thing is what we refer to as a cumulative distribution function. So far I had defined what is probability x equal to xi. So suppose I know that x takes values x1, x2, x3 with x1 less than x2 is less than x3. That is, I have an order of x taking values x1, x2, x3. Now this cumulative distribution function is a function that is defined on the entire real line to 0, 1. It is a function that maps the entire real line to 0, 1. And how is it mapping? For any a in this real line, that is minus infinity to infinity, it defines f of a to be probability x is less than or equal to a. Is the definition clear? Why is it cumulative? For example, if I have x1 equal to 1 and x2 equal to 2 and x2 equal to 3, what is probability? And it is 0. Otherwise, what is probability x is less than or equal to 0?
0.
It is 0. But what is probability x is less than or equal to 1? I need to know what is it is going to be probability of x1.
X1.
Right? What is probability x is less than or equal to 2?
Probability of X1 plus X2.
So that is where you are accumulating. Okay, this is where you are adding up or accumulating. That's why it is called a cumulative distribution function. Any questions still here? Yeah, is this clear? Now, what is the shape of a cumulative distribution function for a discrete random variable? Now, when I look at a discrete random variable, for example, I have this discrete random variable here, where x is taking 1, 2, 3, 4. The first thing I verify is, okay, 1 is less than 2, is less than 3, is less than 4. My x1 is less than x2, is less than x3. What is probability x is less than or equal to 0?
M0.
It is 0. So for any value, the first value it takes is 1. So for any value of a which is less than 1, the probability is going to be 0. Would you all agree? Yeah?
Yes, ma'am.
Right.
Yes.
So suppose I'm going to plot here the value x takes and here what is fa till it hits 1. Okay. Till it hits 1, I'm going to have f of a to be 0. Would you all agree? At x equal to a, what is the probability x equal to 1? It is
1 by 4.
1 by 4.
Okay. What would be the probability x is less than or equal to 1.5?
1 by 4.
It would be again 1 by 4. X is less than or equal to 1.9?
1 by
1
4.
by 4.
Again 1
Again
by 4.
1.4. So it will continue to be 1.1 by 4. At x equal to 2, what would be the value? It would be 1 by 4 plus 1 by
1
2,
by 2.
which is 3 by 4. Is that clear?
Yeah.
And that would continue till 3. At x equal to 3, it would be 3 by 4 plus 1 by 8, which is 7 by 8. It will continue till to be 7 by 8. So this is 3 by 4, this is 7 by 8. And x equal to 4, it will become 1. And it will continue to be 1 for any value beyond 4. This is what we refer to as a cumulative distribution function. And for any discrete distribution function, the cumulative distribution function resembles what is called a step function or a stair function with this as the points of discontinuity. Okay. So I have what is called a step function where I have this is actually cutting out and it looks like a stair. So this is what we refer to as a stair function. But remember, the values of f of a is bounded by 0 and 1. It will, beyond this, it is going to remain at 1 no matter what is the value. Is this conceptually clear? What is a step function and a cumulative distribution function?
Yes, ma'am.
Yeah, right. Now the next thing is, so we started by what was a random variable. Then we talked about what was a probability mass function. Then we talked about what is a cumulative distribution function. Now, two of the things that are very important for us when we talk about random variable is the concept of an expectation and a variance. Okay. Now, what is expectation of a random variable? For example, let me talk about the experiment of tossing a coin once. What are the values or what are the outcomes of this experiment when I toss a coin once?
Head and tail.
Head or tail.
It is head or tail, right?
Tail.
I can put this, I can map head to 1 and tail to 0. Is that clear? Okay. Now, what is going to, suppose I'm going to toss this coin 10,000 times. Okay. So what are the values this x is going to take? X takes the value 1 or 0. with probability half and half if it is a fair coin or an unbiased coin? Would you all agree?
Yes, ma'am.
Yes.
Right? So now I am interested in knowing what is the long run average of the value of the random variable. That is, if I keep tossing this coin some 10,000 times, the random variable can take the value 1 or 0 with chance half and half. So I'm interested in knowing what is the long run average. And this long run average is what we refer to as the expectation of a random variable. So if x takes the value 1 and 0 with probability half and half, the expectation of x is 1 into half plus 0 into half, which is half. It doesn't mean that this random variable is going to take a value half, but it only means that the long run average of the value of the random variable. And what is the value of the random variable? It takes either the value 1 or 0 in repeated. Suppose I'm going to repeat the experiment in similar conditions many times, then the expected value of this is given as 1 by 2. That is the biggest notion of expectation. Is this clear? It does not mean that your x would take that value. It is the long run average of the value the random variable would take. Is this clear?
Yes, ma'am.
Yes, ma'am.
Right? Okay. Now, this random variable or the expected value can also be viewed as the weighted average of the values. Okay. What do we mean by weighted average? You see that xi is the value the random variable is taking, and probability x equal to xi is the weight I assign with the value x equal to xi. So in other words, the expected value or the expectation of a random variable can be viewed as the weighted average of the possible values. Now, suppose I give you a random variable, x takes the value 0 with probability 1. So let me give you a random variable. X takes the value 0, probability 1. Y takes the value -2 and 2 with probability half and half. Z takes the value -20 and 20 with again probability half and half. What is the expected value of x?
0.
What is the expected value of y?
0.
Okay, so 0.
0.
What is the expected value of z?
0.
0. Okay.
0.
But then if I say just the expectation of x, y, and z is equal to 0, something that you notice is which variable has a higher spread?
Z.
Z variable.
Z.
Z has a higher spread. So analogous to my mean and variance, I need a measure for spread. And that measure for spread is what I refer to the variance of a random variable. So what is the variance of a random variable? The definition is if x is a random variable with expected value mu, the variance. So if you look at this term, x minus mu, x minus mu is nothing but the deviation of my random variable from the expected value. I am looking at the square and I'm looking at the expectation. Again, expectation is nothing but the weighted average or the sum of square deviations. So you can see that the variance of a random variable is nothing but expectation of x minus mu whole square. Okay. Now, one of the things that always helps us when we are asked to do problems of this kind is a computational formula for variance. What do we mean by computational formula for variance? I can write this expectation of x minus mu square as expectation of x square plus mu square minus 2 times expectation x mu. Would you all agree?
Yes, ma'am.
Yes.
Now, I also know from my properties of expectation of A times X is A into expectation of X. That is, if I multiply my random variable with any scalar, expectation of A times that is going to be A into expectation of X. If X and Y are random variables. Expectation of x plus y is expectation of x plus expectation of y. That is, expectation of sum is sum of expectation. Okay, let's apply these two properties to find out this. What is expectation of x square plus mu square? This is going to be expectation of x square. Expectation of a constant is going to remain a constant. Minus 2x mu is going to be minus 2 times expectation of x and mu. I add this and I get it is expectation of x square plus mu square minus 2 mu into expectation of x. But what is expectation of x? It is mu. So I get this as expectation of x square plus mu square minus 2 mu square to get a computational formula for variance, which is nothing but I can compute variance as expectation of x square minus mu square. Is this clear? The computational formula for variance of x?
Yes, ma'am.
Right?
Yes, ma'am.
The basic is this is for any random variable, and in particular, we told for a discrete random variable. The first thing is we always understand what is the probability mass function. We need to understand what are the parameters of this distribution, and then we will find out what is the expectation, what is the variance of the random variable. So let's start with the most basic random variable, discrete random variable, which is called a Bernoulli random variable. So what is a Bernoulli random variable? A Bernoulli random variable is defined to be a random variable which takes either the value 1 or 0. So why is it called a Bernoulli random variable? So many a time, let's tell what is a Bernoulli experiment. A Bernoulli experiment is an experiment which has only two outcomes. Okay, so when I toss a coin, what are the outcomes?
Head or tail?
Head or tail. So that is a
Excuse
Bernoulli.
me, ma'am.
Yes. Yeah, please go ahead. Yes, please go ahead. Hello. Okay. So
Sorry for the disturbance, ma'am.
yeah.
My internet just went gone.
Okay. Yeah. Yeah. So
So,
ask me.
ma'am, from which week this content is?
This is the distribution, random variable and discrete and continuous distributions. Okay.
So it's from week third maybe.
Swati, can you answer this question?
Uh, uh, it's from week 9 to 12. The revision session is from week 9 to 12.
Yeah.
So, okay, ma'am. Okay.
Okay. Right. So now what is the idea of a Bernoulli and where can you apply this Bernoulli? So see, it is not necessary that always my outcome should be only two. For example, if I roll a die and I define an event to be a success if I get an odd number and a failure if I get an even number, then what is the event of getting my odd number? It's going to be 1, 3, and 5. And probability of getting an even number. So I can define success to be an odd number, failure to be an even number. Even that would be a Bernoulli random variable. Is it clear?
Yes, ma'am.
Yeah, ma'am.
Yes, ma'am.
Right? So a random variable that wherein I'm mapping my outcomes to either 1 or 0, and 1 or 0 is typically when I could have success or failure. So this could be again, from a business perspective, you could say that if a person makes a purchase, it could be a success. If a person makes no purchase, it could be a failure. And the chance, so that is a Bernoulli random variable. The outcome of making a purchase is a Bernoulli random variable. Is that clear? Okay. So let
Yeah,
X
ma'am.
be a Bernoulli random variable that takes the value 1 with probability P. So then it takes the value 0 with probability 1 minus P. That is what we have here. So it is taking the value 1 with probability P. Okay, and that is what I have here. Probability 0, it is taking the value. So this is P, this is 1 minus P. So what would be the expectation of a Bernoulli random variable? It is going to be 0 into 1 minus p plus 1 into p, which is p. Okay. So what is expectation of x square here? If x takes a value 0 and 1, what is the value x square would take?
0, 1.
1.
That will also take the value 0 and 1. With what probability? What is the probability x square equal to 0?
Same
Same.
probability.
Same, 1 minus
1 minus
p and p. So what would expectation of x square be?
P.
MP.
Also be p. And what do we know about variance of x? We know variance of x is expectation of x square minus expectation x whole square or mu whole square. So I have a p square, p minus p square, which is same as p into 1 minus p. So I can obtain for a simple Bernoulli random variable, I can obtain what is the expected value and the variance of a Bernoulli random variable. Till here is it clear? Expectation is p, the variance is p into 1 minus p. Is
Yes.
this clear? Right.
Yes.
Now the next distribution is again what we refer to as a discrete uniform distribution. Again here I have a random variable which takes values 1 to n. It is called a uniform. First of all, it is a discrete value because it is taking values 1, 2 up to n. That's why it is discrete. What is uniform? The probability that it is equal to 1 is the same as the probability it is equal to 2. It's the same as probability it is equal to n. So you can see that the probability x equal to xi is 1 by n, 1 by n, 1 by n. Till here is it clear?
Yes, ma'am.
Now what is the expectation of x here in this case?
N
It would
plus
be 1 into 1 by n plus 2 into 1 by n plus n into 1 by n, which I can write as 1 by n into 1 plus 2 plus n. What is this? You all know what is 1 plus 2 plus n.
n into
n
n
to n plus 1
n
by
into n
2.
plus 1 by
So
2.
this is n into n plus 1 by 2. So what would be the expectation of a discrete random variable? X
N
uniform.
plus
It would be n plus 1 by 2. Now what is expectation of x square? What are the values x square would take?
1,
1,
4,
4.
9. 9.
and
9 up to n square. With what probability?
1 by
6
n.
1 by n,
Same.
1 by n, 1 by n, 1 by n. So what is expectation of x square?
1 into 1 by n
1
plus
by
4
n into 1 plus 4 plus n
Plus
square.
Yes.
What is 1 plus 4 plus n square?
n into n plus 1 into 2n plus 1 by 6.
By 6. So this n would get cancelled. So expectation of n square would be n plus 1 into 2n plus 1 by 6. Would you all agree?
Yes, ma'am.
Yeah.
Yes, ma'am.
So I have expectation of x square would be n plus 1 into 2n plus 1 by 6. So what would variance of x be?
n plus 1 by 2
2n plus 1 by 6 minus n plus 1 by 2 whole square. Agreed? I'll leave it as an
Yes.
exercise that you can verify that is n square by 1 by 12. So for any distribution, we can find out what is the probability mass function. Now how would the graph of this random variable look? Suppose I have x here and probability x equal to x here. It's taking the value 1, 2 up to n. It is going to look uniform because the values are the same. Would you all agree?
Yes, ma'am.
Right?
Yes, ma'am.
This is how the graph of the discrete random variable would look. Okay. Now we are going to look at the second thing or the most important thing, which is a binomial distribution. To understand what is a binomial distribution, we go back to our Bernoulli experiment. We have already said that a Bernoulli experiment is an experiment which has only two outcomes, which is a success and a failure. Would you all agree? Till here, is it clear? Right.
Yes, ma'am.
Now, when
Yes.
I toss a coin twice
Yes,
and I say head is a success and tail is a failure, okay, I know that it is a single Bernoulli random trial. I call tossing a coin once as a Bernoulli random trial. Now, if I toss a coin second time, okay, will the probability of me getting a head change? or will
No.
it remain
No,
the
ma'am.
same?
Will be same.
Same.
It would remain the same, right? And so the probability of me getting the head would remain the same. Will that depend on whether my first toss was a head or a tail?
No.
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 So what I define here, or what we have just discussed, is a collection of two Bernoulli trials that are independent, where the outcomes are independent of each other and they are identical with each other. Is it clear? Independent, because whether I get a head or tail in the second toss does not depend on whether I get a head or tail in my first toss. Till here, is it clear? And identical because the chance of me getting a head in the second toss is the same as the chance of me getting a head in the first toss. This is referred to as IID trial. Till here, is it clear?
Clear,
Yes,
ma'am.
ma'am.
Yes.
Right? So now what I discussed for 2 trials, I can extend it to 10 trials also. Right? So I can call a collection of random variables as independent and identically distributed, IID, if the random variables are independent and they share a common probability distribution. Okay. So now let's go back to our Bernoulli trial. I have now, suppose in my Bernoulli trial, I have 2 independent trials where each is a success with probability P. Okay. So my N is 2. Okay. And I have a success with probability P and failure with probability 1 minus P. So what are the possible outcomes? It is success, 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 failure, failure, success, and failure, failure. Would you all agree?
Yes.
Yeah. Now, let me define X to be the number of successes that happen. What is the value that you'd associate with this outcome? 2. Here,
1.
here,
1.
1. Here,
0.
0. So this random variable X takes the value 0, 1, and 2. So I'm counting the number of successes that occurs in 2 trials. I need to know what is the probability of success. So this N and P are referred to as the parameters of the random variable. And this random variable X that counts the number of successes is referred to as a binomial random variable. Till here, is it clear?
Yes.
Okay. So now what is our point? Suppose I can, whatever I did for 2, I can extend that to n trials or 3 trials or 4 trials. But what I want to know, what is the chance of me getting a success? So let's look at 3 trials. Okay. What are the possible outcomes? I have success, 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 failure, success, failure, success, failure, success, 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 failure, 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 success, failure, 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 success. Okay. And then I have a failure, failure, failure. Is this right? These are the possible outcomes. Now let me look at what are the number of successes. How many successes do I have in my first outcome?
3.
3. Here,
2.
2. Here,
2.
here,
1.
2, right?
One.
Oh, sorry. 2.
Here it is 1, 1, 1. Here it is a 0.
0.
Now let me look at what is the probability X is equal to I. Okay. Now what is the probability of me getting 3 successes? It is the same as probability of a success, P into P into P. Why is it P into P into P? I know that the probability of success in my first trial is same as the probability of success in the second. It is same as probability of success in the third, and they are independent. So I go back to my multiplication rule. If it is independent, it is a product of probability. So it is a P into P into P. Till here, is it clear?
Yes.
Now what is it for here? It would be P into 1 minus P. This would be P into 1 minus P into P. This would be 1 minus P into P into P. This is P into 1 minus P into 1 minus P. This is 1 minus P into 1 minus P. This is 1 minus p into 1 minus p into p. And this is 1 minus p into 1 minus p into 1 minus p. Is this clear? Yeah.
Yes.
So I can
Yes.
see that what is the probability x equal to 3? That is, if I have 3 trials, the chance that all 3 of them are successes are p to the power of 3. Agreed?
Yes, ma'am.
Yes, ma'am.
What is probability x equal to 2?
P square.
P square.
P square
P
1 minus
square into
1
Minus
minus P.
1 minus p. But how many times is it appearing?
3 times.
3 times. So it would be 3 into p square into 1 minus p. Do you all agree?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
What is probability x equal to 1?
It would be 3
P
Into p
1
into
into 1
1
minus
minus p.
P into 1 minus. Yeah.
And probability x equal to 0 is 1 minus
Minus
p
P
whole
cube.
whole cube.
Is that clear? Okay. So now you look at the, so what, suppose I have now 4. Okay, tell me what would, and that is n equal to 4, p remains p. What is probability x equal to 4 in that case? If n equal to 4 and p is just equal to p, what would n equal to 4 be?
It would P to the power 4.
P to the
To
power
the power of 4.
P
What
to the
would
power
x
4.
equal to 0 be?
1 minus P to the
Minus
power.
Minus P to the power
What
4.
would probability x equal to 3 be?
Ma'am, 4 into
4 into
P to the power 3. 1 minus P to the
From
power
where did you get that 4? So I know that there are going to be, so that is where I introduce what is the binomial formula. Okay. And what is the binomial formula? The binomial formula says that the probability x equal to I, this portion is clear. P to the power of I into 1 minus P to the power of n minus I.
Yes.
Yes. This n choose I is how many times I can have this. So if I go back to this, the success could have been in the 3rd position or in the 2nd position or in the 1st position, right? 3 choices. So that was 3. Is that clear? So 3 choose 1 or 3 choose 2. In general, it is called n choose I. Till here, is it clear? Now, what are the values this I will take? What are the values I takes? I can take
Ma'am, I will take 0 to n.
0, 1, 2, up to n. So this complete thing completes our formula for the probability mass function, which says that if I have a binomial experiment with n independent trials and p the probability of success of each trial, then probability x equal to I is equal to n choose I, p to the power of I into 1 minus p to the n minus I. Any questions till here? Is it clear?
Clear,
Yes,
ma'am.
ma'am.
Okay. So now what you need to know, whenever you are asked a problem, first, if you want to apply it as a binomial distribution, check the IID condition. That is very important. Okay. Once you check the IID condition, then you understand what is this n and p and just plug in the formula. Is this clear? Right. So let's look at how the distribution looks like. If p is equal to 0.5, so you can see that if p is equal to 0.3 and n equal to 4, this is the distribution. So what can you say about this distribution? It is right skewed. Is that clear?
Yes, ma'am.
Right.
Yeah.
Now, if I look at p equal to 0.5, you see that this is my distribution, which is symmetric. And if p equal to 0.8, you see that this is my distribution, which is left skewed. Which leads me to tell that if my probability, that is, if the shape, a binomial distribution is right skewed if p is less than 0.5, it is symmetric if p equal to 0.5, and it is left skewed if p is greater than 0.5. Is this clear?
Yes.
Yeah, ma'am.
Yeah. Okay. So now once we know about a binomial distribution, we demonstrated for a small value of n. Now the natural thing would be what would happen if my n becomes really large. So let's look at what would happen if my n becomes large. So let's look at what happens when n equal to 40. Instead of n equal to 4, let's look at what happens when n equal to 40. What do you notice here? It appears to be symmetric, but it is actually not symmetric. But what do you note? What is this one? You see, it is shifted to the left. Do you see that? Now, if p equal to 5, you see that the mean is around 20. When it is p is equal to 8, you see the same distribution. The distribution patterns remains the same, but it is shifted to the right. Do you notice that?
Yes, ma'am.
Yeah.
Yes,
So
ma'am.
now the
Yeah,
next
ma'am.
thing is, what is the effect? The effect is, if I have a small n and p, for large n, the binomial distribution, whether whatever is the p, it approaches symmetry, it looks symmetric, right? Whatever it was for 0.8, 0.5 and 0.3, it appeared to be symmetric, right?
Yes,
The
ma'am.
distribution was this one. So I can tell that from my observation. Again, remember, we are not proving anything here. From my observation, for large n, the binomial distribution approaches or appears to be symmetric. Is this clear? Yeah?
Yes, ma'am.
Yes, ma'am.
Okay. Right. Now, the next thing is, what is the expectation and variance of a binomial random variable? That is the most important thing. Now, see, one way to write it is, I have x, which is my random variable. I write this x as, this is a symbol that I am going to use when I say it is distributed as. It is not n. It is typically used for distribution. I say it is a binomial with parameters n and p. Okay. What is the probability mass function? Probability x equal to I is n choose I, p to the I, 1 minus p to the n minus I takes value 0, 1, 2, up to n. Till here, is it clear?
Yes, ma'am.
Yeah, ma'am.
Now we want to know what is the expectation of this random variable. Remember, this x is counting the number of successes in n trials. Is that right? Okay.
Yeah, ma'am.
So
Yes,
I can write this x as x1 plus x2 plus xn, where each xi is an independent Bernoulli trial with probability of success p and probability of failure 1 minus p. Would you all agree that I can do this? I
Yes,
can
ma'am.
express x, which is the sum of successes, to be x1 plus x2 plus xn, where each xi is a Bernoulli random variable and x1, x2, xn are independent of each other and have identical distribution. Would you all agree with this?
Yes, ma'am.
Right. Now, what is expectation of x1 plus x2?
Mm.
Expectation of
Expectation of
x1
x1
plus
plus
x2.
expectation of x2.
x1, expectation of x1
X1 plus X2.
plus expectation of x2, right? So what would expectation of x be? It would be expectation of x1 plus x2 plus xn. Each one of them is a Bernoulli random variable. What is the expectation of x1? If x1 is a Bernoulli with parameter p,
P.
P.
is p. So I
P.
have p plus p
A
plus
plus n times
p
of
n
p.
times. So what is the expectation of this
Ma'am,
random
NP.
variable? It
N.
is n
N into P.
p. So that is how I can obtain the expectation of a Bernoulli random variable to be n into p. Till here, is it clear?
Yes,
Yeah,
ma'am.
ma'am.
Right. Now, if I have two random variables x and y and they are independent of each other, I know that the variance of x plus y is variance of x plus variance of y. This is another property of variance. Okay. So what would variance of x plus y plus z be? It would be sum of variance of sum is sum of variances if my random variables are independent. Is this clear?
Yes, ma'am.
Yeah,
Right?
ma'am.
Okay, so now let's look at what would be variance of x. Variance of x is going to be variance of x1 plus variance of x2 up to variance of xn. But what was variance of x1? Bernoulli. This was P into 1 minus P.
P into 1 minus P.
Plus P into 1 minus P. Plus P into 1 minus P. So how many times am I adding it? I'm adding it
n number of times.
So I get the expectation and variance of a binomial random variable to be n into p is the expectation and variance is n p into 1 minus p. Till here is it clear?
Yes, ma'am.
Okay. So the binomial random variable, the two key things that we need to understand is I independent and identical, IID. And then the expectation of x, the parameters of the distribution are n and p. The probability mass function is n choose I, p to the power of I, 1 minus p to the n minus I. Expectation is n into p. The variance is n into p into 1 minus p. Till here is it clear? Binomial is a very, very important distribution. Is this clear?
Yes, ma'am.
Okay. Now, one of the biggest limitations of the binomial distribution was the independent nature of the trials. Okay. But suppose I give you a trial of this kind. When I'm tossing a coin, I know that I can have the independent nature because head and tail in the first toss and head and tail in the second toss are independent of each other. On the other hand, if I give you something of this kind, okay, where I start with a bag with 4 white balls and 3 black balls. I pick up a ball at random. I don't replace the ball. So if it is a black ball, what would my bag have? If it is a black ball.
2 balls.
If it is a black ball, I'll have only 4 white and 2 black balls. Is it right?
Balls.
If it is a white ball, I'll have 3 white and
balls.
3 black balls.
Black balls.
Now, in the first trial, what is the probability or chance of me picking up a black ball?
3 by 7.
3 by 7. What was the chance that I was picking up a white ball?
4 by 7.
4 by 7. Now, let's look at the second trial. What is the chance that you pick up a black ball in the second trial?
2 by 6.
2 by 6.
2 by
The
6.
chance that you have, so the chance that you pick up a black ball in the second trial, does it depend on the outcome of your first trial?
Yes, ma'am.
Yes.
It
Yes,
depends.
ma'am.
So what is the condition that is violated from a binomial experiment here?
Independent.
It is
Dependence.
It is not independent.
independent.
It is not identical.
Identical.
Is it clear?
Yes, ma'am.
Yes.
Yes.
Yes, ma'am.
Okay. So what is the whole, how do we model situations of this kind? We move to what is called a hypergeometric distribution. Okay. Now in a hypergeometric, give me a minute. In a hypergeometric distribution, the population is again dividable or divided into 2 independent subsets. In the example that we saw was black and white. Okay. And here I am losing my IID or the identical distribution. Is that clear? In other words, what you're doing here is you're sampling without replacement. Till here, is it clear?
Yes, ma'am.
Yes, ma'am.
Okay. So
Yes,
once
ma'am.
I have a hypergeometric distribution, let's understand what is the random variable here. So suppose I have a random variable here. So what is the random variable? I have a fixed number of trials. The probability of success is not the same from trial to trial. And I'm defining here the number of successes out of the total number of items chosen. So let's look at what is the pictorial representation to understand what is hypergeometric clearer. Suppose I have a total of capital N balls. Okay, of which how many are black? Small m, right? Of which small m are black. Then how many would be white? I'd have capital N.
Capital N
minus M.
Minus M.
Okay. From this n balls, I am sampling small n. So this capital N could be 50. The small n could be, say, 10. Is that clear?
Yes,
Yes,
ma'am.
ma'am.
Okay, so this could be 50. This could be 10. This could be 25. What would this be? This would be 25. Is that clear? Now I'm interested in this sample of size 10. How many black balls can be there? What is the possible values this X will take?
0 to 10.
Can it take the value 0?
Yes.
Can it take the value 1?
Yes.
Yes.
Yeah, it can take the value 2. So what is the probability it takes the value 0? So how many ways can I choose 10 balls from 50 balls?
T choose 10. Sorry, 10 choose
50C 10.
50C
10.
10, right? I can choose 10 balls from 50 balls and 50 choose 10 ways. This is the total number of outcomes in my sample space. Would you all agree?
Yes, ma'am.
Yes, ma'am.
Out of this, how many I want X equal to 0. What does X equal to 0 mean?
Ma'am, choose nothing.
No
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 black
black ball.
No
No black
black.
ball.
Right, so from these 25 balls, I'm having no black balls, and all of them are from the 10, right? All the balls are from white. Is it clear?
Yes, ma'am.
What is the
Yes, ma'am.
probability X equal to 1?
25C1.
25C1 into 25C9.
9. And what would be the denominator?
50C10.
It
50
would be
seater.
50C10. Is that clear? Now
Yes.
I can generalize that to probability. This n choose n is my denominator. M choose x and n minus m choose n minus x, and x takes value 0, 1, 2 up to n. Till here is it clear?
Yes, ma'am.
Now
Yes, ma'am.
suppose I had 45
Ma'am,
and 5. And again I'm choosing the number of black balls. What are the values this x will take?
Using 10 balls again.
Yes.
So it would be
The denominator would remain the same, or will that change?
90 choose 10, and above will be
90
45.
choose 10. Why will it be 90 choose 10? I'm having 50 balls, but 45 black and 5 white,
Okay. Then 50 choose 10. I thought it is 45, 45.
right?
Then above would be 45 choose
What are the
10.
values x can take here?
0 to 10. 0 to 10.
What does x equal to 0 mean?
No black balls.
Then what would all of them be?
That would be all.
All of them are?
Okay. 0
White.
cannot, is not possible.
Can all of them be white balls?
No.
No.
That is what I want you all to think about. Okay, I'm not going to solve the problem, but is this clear? This
Yes, ma'am.
x equal to 0 up to n has some condition. Is that clear?
yes, ma'am.
Yes, ma'am.
So this is something that you need to understand. Okay. So now suppose I have 7 balls. Okay. And I'm choosing 2 out of them. 4 are white, 3 are black. 7 balls. Okay. 4 are white, 3 are black. Is it clear? I am choosing 2 from these 7. What are the values x would take?
0, 1, 2.
0,
Number
1,
of
2.
black balls. I'm looking at number of black balls.
0, 1,
0, 1, 2.
2. And what would be the denominator here?
7C.
7C2.
7C.
So I can come up with my probability mass function. Is it clear?
Yes, ma'am.
Right?
Yes, ma'am.
So now the next thing is, what is the expectation and variance of a hypergeometric distribution? You can show that the expectation is n into m by n and the variance is n into m by n into this quantity. I just want to focus on this for now. Look at n into m by n. I can write this in this form.
Yes, ma'am.
Similarly, I can write this as n into m by n into 1 minus m by n. Can I?
Yes, ma'am.
Into, I can write this as 1 minus n by n into 1 minus n by 1 by n. Can I do that?
Yes, ma'am.
Yes, ma'am.
Now, if this capital N is really, really large, okay, what would happen to this term?
Become 1.
It will become 1. Now, does this resemble something in that case?
Yes, n into probability and 1 minus
1
probability.
minus probability. What was this? N
Binomial
into,
distribution.
it was your variance of your binomial distribution, and n into p was the expectation of your binomial distribution. Is this clear? Okay,
Yes.
Yes,
so
ma'am.
let's draw the PDF of hypergeometric for different values. Okay, so now if you look at n equal to 20, m equal, so what are the parameters of a hypergeometric? It is capital N, it is small n, and it is m. Okay, so these are the parameters of the hypergeometric. N equal to 20, you see this is what happens. This is when it is symmetric. But what is the interesting part is, once I keep increasing my n, okay, what do you see it is happening to the distribution? It's becoming symmetric in some terms,
Yes.
right?
Yes,
Not
ma'am.
only is this becoming symmetric, I show that for a particular value of n and p, okay, as n increases, you see the binomial and the hypergeometric are almost similar. Do you see that? The red is the hypergeometric, the blue is the binomial. And that is even more clear in this. Is that clear?
Yes, ma'am.
Yeah. So you can see that at some point it converges to a binomial. So depending on this capital N, if N is sufficiently large, the distribution looks like a binomial distribution. And you see here, when both I have N, small n is large and capital N is large, you see that it almost resembles what we call a bell curve. You'll be learning more about the bell curve in statistics too. But this is something that you need to observe. Is this clear?
Yes, ma'am.
Yes, ma'am.
Right. So the next thing which we want to understand is, so when we came to discrete distribution, we looked at the Bernoulli, we looked at the binomial. Before the binomial, we looked at discrete uniform. And then after binomial, we looked at the hypergeometric, because we established how the hypergeometric is different from the binomial distribution. Any questions still here? Is it clear?
Yes, ma'am.
Okay.
Yes, ma'am.
Yes,
Now, the
ma'am.
next distribution that we are going to look at, and this distribution is what we call the Poisson distribution. Now, many a time we might be interested in counting the number of events that happen either in an interval of space or in an interval of time. What do we mean by that? For example, if I'm interested in knowing how many people have entered a superstore from morning to afternoon. Okay, so what is my, first of all, is it discrete or is it continuous? I'm interested in knowing number of customers who enter a place during a given time, that is in the morning to afternoon. Will it be continuous or discrete?
Discrete.
It is
Discrete.
discrete
Discrete.
because I'm looking at counting the number of people. Okay, now if I want to know the number of people who have entered a bank between 9 in the morning and 12 in the or 11 in the morning, that will also be discrete or continuous.
Continuous.
Number of
No,
people
time. Number of people discrete. Time
it
continuous.
is to be discrete. So whenever I'm interested in knowing or I want to model situations which are dependent or which is counting the number of events that happen either in a fixed interval of time or space, I model it as a Poisson distribution. For example, how many spelling mistakes are there in a complete paper? Number of mistakes. Again, I'm counting the number of mistakes. Here I don't have fixed interval of time, but I have a fixed interval of space. Is this clear?
Yes, ma'am.
Yeah.
Yes,
So
ma'am.
we call this a Poisson distribution. The parameter of the Poisson distribution is nothing but these events happen with a known average rate lambda. And again, it is independent of the time since the last event. So this is important. I'm counting the number of events. So I have a Poisson distribution where I give the probability of Poisson x equal to x. What are the values this x can take? If I'm counting the number of people who enter a shop between morning 9 and 12:30, what are the values this x can take?
0 to
0 to n.
0 to
n.
N.
what is n?
0 to
I mean,
What would n be?
It can be any number.
it can be any number.
So it just takes, that's why you can see that x takes the value 0, 1, 2. It is countably infinite. Is it clear? Yes. Number of telephone calls received per minute. Will it be a Poisson distribution or not?
Yes.
Yes, it will
Yes,
be
ma'am.
Is it interval of time or interval of space?
time.
Interval of time.
Interval of time.
Number of defects in a roll of cloth.
Ma'am, not Poisson distribution.
Why not?
Because it is not
Defect
time
per
dependent.
number of defects per meter in a roll of cloth.
Space. Yeah.
Space.
Yes, ma'am, because
Number of
space.
space.
It is interval of space.
Is it Poisson or it's not Poisson?
Ma'am, it is
That's
Poisson. It is Poisson.
Interval of
Interval of
Space.
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 number of vehicles passing through an traffic intersection in the morning.
It's
It is
Interval of
Poisson.
time. Poisson.
interval of time.
Again, Poisson. Is that clear? So we first
Yes, ma'am.
understand what are the, so when can I model anything as a Poisson? And for a Poisson random variable, what is the expectation of a Poisson? So first I need to understand what is the expectation and the variance of a Poisson. But before that, what is the probability mass function of a Poisson distribution? What is the probability mass function? Probability x equal to x is e to the power of minus lambda, lambda to the power of x by x factorial. Is that clear?
Yes, ma'am.
Where what is this lambda? It is nothing but the average number of events per interval. Okay. Now the expectation and the variance are of a random variable is both of them. If it is x is a Poisson with parameter lambda, both the expected value and the variance is equal to lambda. Is any questions here? Is this clear?
Yes, ma'am.
So let's test a few concepts. Okay, let me give you an example. Please note it down. The example I'm going to give is I have a superstore. It's an e-commerce company. Okay, take it to be Myntra or Nike or anything of that kind. It is observed that 10% of the customers return the items purchased by them. I repeat, it is observed that 10% of their customers return the items purchased by them. On a particular day, 20 customers purchased items. Okay. Now, what is, if I want to model the number of customers who return the item, what will be the distribution? I'm observing that 10% of the customers return item, and on a particular day, 20 customers purchased items from this company. Okay. What would be the probability that exactly 5 customers would return the item? What would be you model it as?
Binomial.
Okay. What all do you want to know? What are the parameters of a binomial distribution?
Number of trials and how many, what is the P, like probability of return.
What is the number of trials in this case? On a particular day, 20 customers.
20 customers.
N equal to 20. What is the P here?
It's 0.1.
0.1. But what do you have to check if you have to model it as a binomial distribution?
How many returns? So it would be 0.9 here.
No, but there's something else. How would you, what do you mean by IID here?
Okay, IID is customer, every customer is independent, their purchases are independent.
Return made by every customer is going to be independent of each other and with the same probability. Is that clear? Independent and identically distributed. Is it clear?
Yes,
What
ma'am.
is the average number of customers who are likely to return the items? What is your N here?
N is 20.
20. What is P?
P is 0.1.
0.1. So what is your, on an average, how many customers will return?
2.
2. 20.1, which is equal to 2. Is this clear? Is this clear, please?
Yes, ma'am.
Yeah. Okay. Now let me say on an average, okay, 20 customers cancel their orders placed at this portal. I repeat, on an average, 20 customers per day cancel their orders. What is the difference between this and the earlier thing? What am I counting here?
The subset will be number of
Where you get the average you already provided for a
So
certain
I'm
case.
telling on an average, 20 customers per day cancel their orders. Okay. I want to know what is the probability that the number of cancellation is exactly 20.
This is
What do
Poisson.
you model it
This
as?
is Poisson.
Poisson
Poisson
distribution.
model.
Poisson. What is the lambda here?
20.
20.
Because 20 is on an average, 20 customers cancel their order. Is this clear?
Yes, ma'am.
Okay. So,
Yes, ma'am. Ma'am, I have one question.
hmm.
Ma'am, the previous question, just to this one, that you asked that the five people or they will be cancelling it on an average. Ma'am, there you said 20 into 0.1, that is 2.
Yes.
But n into p, right? N into p is the formula for E
Yes.
of x of binomial distribution.
Yes. Yes.
So
Yes.
that only we are referring to as on an average, right?
Yes, that is average number of customers in the earlier setup. But in the second setup, what am I telling? I'm telling you on an average, I'm already saying per day, 20 customers cancel their order. So what
Okay.
would you model it as?
Yeah, this will be Poisson.
A bit Poisson. Is that clear? The same situation, but in one case, you model it as a binomial. In another case, you are modeling it as a Poisson. Is that clear?
Yes, ma'am.
Okay.
Understood.
That is what we wanted to check. Okay, so when we are looking at discrete distributions, we started with the Bernoulli, then we went to discrete uniform, then we introduced the binomial, the hypergeometric, and the Poisson. Any questions, clarifications? Is it clear?
Ma'am, I just wanted to understand one thing.
Yeah.
There is a graph given of a PMF for this Poisson distribution, right? Let's say there is x1 and x2. How to identify whose lambda is greater or in Poisson distribution from the graph itself? Is there any way we can do so? Like
I
we
think
are comparing we are comparing two random variables, right? X1 and X2, and both belong to the Poisson distribution from a
So you
graph.
can look at it now. What would happen if your lambda is 0.5? You just pick that up and plot that graph for a lambda given everything else. Only lambda is changing here. How would you
Yes,
just
yes,
look at what would happen? Only lambda changes, right? Do it for lambda equal to 1, do it for lambda equal to 2, and then you learn it yourself.
So I came across a question where a graph is given of x1 and x2. They are asking to comment about lambda on that. So
Exactly. I'm not going to, I told you earlier itself that I'll not answer specific questions, but what I'm trying to tell you is for different values of lambda, you can plot this, right? For x equal to 0, 1, 2. And then you can check what is the distribution. Is that clear?
okay.
Because I know what is the distribution. What is the distribution? The distribution is probability x equal to x. Okay, this is what I have, right?
Yes,
For
ma'am.
different values of lambda, lambda equal to 1 and 2, I can plot this and I can find out how it changes as lambda increases. Would you agree with me?
Okay.
Right? Okay. So
Thank
this
you.
was about the discrete distributions. Any questions? Any questions? Okay. The next thing that we are going to see is a continuous distribution. Okay. Now, when we looked at discrete distribution, what happened was I was looking at probability x was taking values x1, x2, xn, discrete integer values. Okay. But now I'm not interested in what x is taking a value x1, x2, xn, but rather what I'm interested in is what is the probability of x belonging to an interval a to b. Is it clear? Earlier, I was interested in probability x takes a value xi. First, is this distinction clear? Between this is discrete, this is continuous. So what am I asking now? What is the probability that the random variable belongs to an interval, rather than asking what is the probability that x takes a particular value? Is this clear?
Yes.
Right?
Yes, ma'am.
Okay. So now, just as we had a discrete uniform where I knew that x takes value x1, x2, xn, and each one of them with same probability, in the continuous case, I say that x belongs to a particular interval a, b. For example, I have a and b. Okay. And I know that the probability x belongs to this interval is what I'm interested in knowing. So I have in this case what is called a probability density function instead of having a probability mass function. Is that clear? So this, when I have a continuous random variable, I refer to as probability density function instead of a probability mass function. Is this clear?
Yes.
Yes, ma'am.
Okay. Right. So now when I have a probability mass function, I need to know what is the probability density function. Okay. Now what is uniform? It means that for any value of x between a and b, this probability density is a constant. That's what the graph is telling me. Is that clear?
Yes, ma'am.
So this is my k. Would you all agree?
Yes, ma'am.
Right? This is my b and a. So what is this value? This is b minus a. Is that right?
Yes, ma'am.
Yes,
Right?
ma'am.
Okay. Now, just as I had probability of x equal to xi over all values of xi should be equal to 1, here I have over a to b, your fx dx should be equal to 1. Here my summation is replaced by my integration sign. Till here, is it clear?
Yes.
Yes, ma'am.
Any questions? Right. Now, what is the integral a to b f of x dx? It is nothing but the area under this curve. Would you all agree with me?
Yes,
Integral
ma'am.
a to
Yes,
b f
ma'am.
of x dx is just the area. What is the area of this curve in terms of k, b, and a?
Integration of
Integration of 1 by b minus a
No, no,
dx.
I'm not asking integral. Just by looking at this, this is k, this is
AB into K.
b
A
minus a,
into
k into
B, AB.
b
A,
B
minus
minus
a.
A.
B minus A.
What should the area be equal to if it is a PDF?
1.
This should be equal to 1. So what would be my k?
1 by b minus a.
It will
1
be
by B
1
minus
by b minus a. In other words, I have my probability density function, which is given by f of x equal to 1 by b minus a for x's between a and b. Till here, is it clear? Now,
Yes,
a
ma'am.
word of caution here. Some of the books will give a is less than x is less than b. The thing is, when you talk about a continuous random variable, the probability x takes any value is equal to 0. I only talk about x belonging to a particular interval. Is that clear? Okay. So this is the probability density function, which is 1 by b minus a. For any a is less than x is less than b, I have f of x here. I have my x here. Is this clear?
Yes, ma'am.
Right?
Yes, ma'am.
Okay. Now, how do I verify it as a PDF? What was it I verified in my PMF? I verified whether probability of xi was greater or equal to 0 and summation probability of xi was equal to 1. This is what I verified for a PMF, right? Agreed? So what is
Yes,
the
ma'am.
equivalent I would verify here? I'd verify whether f of x is greater or equal to 0 for a is less than x is less than b and integral over whatever range f of x dx should be equal to 1. Is that clear? Now is f of x greater or equal to 0? 1 by b minus a. Is it greater or equal to 0?
Greater than equal to 0.
Right.
Greater.
What is integral a to b f of x dx?
Greater than 0.
What is integral a to b
Greater than 0.
1 by b minus a dx? What would this be?
1.
Ma'am, b
1.
minus a
1.
by b minus a, that
1.
is 1.
B
Pardon?
minus a by B minus a 1.
This is equal to 1. So
Yes, ma'am.
these two conditions have to be checked. If the two conditions are checked, then I know I have a probability density function. Till here, is it clear?
Yes, ma'am.
Right. One of the most important distribution is when A is equal to 0 and B equal to 1, and I have what is called a standard uniform density function. What is a standard uniform density function? It is a function where my A equal to 0, that is the minimum value is 0 and maximum is equal to 1. 1 by B minus A is just going to be equal to 1. And you can easily verify that it is a density function. Till here, is it clear? This is a standard uniform distribution function. Now, the next thing is, what is the CDF of a distribution function? Suppose I have 1 by B minus A is less than X is less than or equal to B. Okay, what is f of X for X less than A? What is the value of f of X for X less than A?
0.
It is 0. For A is less than or equal to X is strictly less than B.
X minus A by B minus A.
You get that?
1 by B minus A.
Again, 1 by B minus A. I look at A to X, 1 by B minus A dx. Is that right? Okay. So I get it as X minus A by B minus A. And for X greater or equal to B, it is going to be equal to 1. Now, if I look at this X minus A by B minus A, you can see that this is nothing but I can write this term as 1 by B minus A into X minus A by B minus A. Do you recognize this equation? Y equal to
mx plus c. It's a slope.
It is mx plus c.
C.
Right? So when I am looking at the cumulative distribution function of a continuous uniform distribution, I get a cumulative distribution which is a straight line. Now this is continuous and this is not like my earlier cumulative distribution function, which was a straight function or a step function. Is this clear? So what is the slope of the line? It is 1 by B minus A. What? Okay, is it clear? And what is the intercept?
Yes, ma'am.
Minus B by B minus A. By B minus A.
Is that clear?
Yes,
How to find the slope and the intercept? Yeah? Any questions? Okay. What is the expectation of a continuous random variable? Now, how did I find the expectation of a discrete random variable? I looked at probability of x and x equal to xi over all I. So similarly, here the expectation would be x into fx dx over a to b. Is that clear? Right? So what would this be? What is my x into b minus a dx a to b? What would I have?
Ma'am, x square by.
So that would be a b square minus a square divided by 2 into b minus a, which will give me a b plus a
Ma'am,
by
b plus a by 2.
Is that clear? So the expectation of a uniform random variable is a plus b by 2. Is this clear?
Yes, ma'am.
What would be the variance? What is
Yes,
expectation of x square? Can you quickly tell me? What would be the expectation of x square? Expectation of x square, I'll have an x square here, right? Right. Variance of x is expectation of x square minus mu whole square, right? Or expectation of x whole square. So what do I get? Can you tell me what would be the variance?
Ma'am, b minus a whole square by 12.
Would be b minus a whole square by 12. You can easily verify because you know what would be your expectation of x square. The expectation of x square is going to be b square plus a square plus ab by 3. And I look at expectation of x square minus expectation of x whole square to get b minus a whole square by 12. Is it clear?
Yes, ma'am.
Right. Okay. Now let's test some concept. I have a standard uniform random variable. Okay. So what is my A and my B here? Standard uniform random variable.
0 and 1.
What is the probability x is greater than 1 by 3?
1.
How? What is probability x is greater than 1 by 3? X is
It should
uniform 0 to 1. Okay.
Ma'am, 1 by 3.
I want probability x is greater than 1 by 3. Will it be 1 by 3? What would it be? It would be
2
1
by
by
3.
3 to 1.
2 by 3.
2 by 3.
1 by 3 to 1 dx, right? What would this be?
2 by 3.
2 by 3.
2 by 3. What is probability? 0.3 is less than x is less than or equal to 0.9.
0.6.
Should be 0.6. Is that clear? So given a value of this random variable, you can actually find out what is the probability. In the lectures, if you look at what we did was, we found out two people coming to meet, okay? And then you can see that this you can go through the lecture notes. I think we, would you want to do this? I'll just give you about 2 minutes. Think about it and tell me how you would model this. What is the randomness here? What is the random variable? What is the uncertainty that you have in this problem here? Are you uncertain or is your friend uncertain?
Friend is uncertain.
Uncertain. So what is the variable of interest here? The time you have to wait.
Wait.
Is that right?
Yes, ma'am.
The time you have to wait is uniformly distributed between 2 p.m. and 3 p.m., which is the same as the waiting time is uniformly distributed between 0 minutes and 60 minutes. Is that right?
Yes, ma'am.
Is that right? So I have a random variable which is uniformly distributed. So the first thing I find out is if x is the amount of time I have to wait, what is the distribution of this x? It is uniformly distributed between
2 and 3.
2 and 3, which is the same as how many minutes are you going to wait?
0 to 60.
0 to
60.
Now, what is the probability that you'll wait for at least 30 minutes?
30 to 6. Integral of 30 to 60.
What would that be? 0 to 60, you know, it's 1 by
30.
And
60.
30 minutes.
It is
30 minutes.
at least 30 minutes is a probability. How can you have 30 minutes?
0.5.
Probability. It's
1
0.5.
1 by 2.
1 by 2.
1 by
Probability that you'll wait for less than 15 minutes.
0.25.
0.25. Very good. What is the probability that you'll wait between 10 minutes and 35 minutes? It would be 5 by 12. And probability that you are going to wait for less than 45 minutes would be 45 by 60, which is 0.75. Is that clear?
yes, ma'am.
Okay. So you can see that we first identify what is the random variable. Here the random variable was the amount of time I'm going to wait. Then I recognize that this random variable is a uniform between 0 and 60 minutes because it is between 2 p.m. and 3 p.m. And then based on this, so the key thing is to identify what is the uncertainty and what is the distribution of that random variable. Once I know what is the distribution of the random variable, I can solve the questions. Is that clear? The question. Any question here?
Yes, ma'am.
Right? Okay. The next thing which we are going to do is a triangular distribution. Now, if I look at a triangular distribution, what you can see is, now this is now 2 p.m. and I'm planning to study for my statistics test until 6 p.m. Okay. So what is the total time I have? Total number of hours?
4 hours.
4 hours.
But then afterwards, you can see that the amount of time I actually spent studying is a random variable. And what is given to me here is the density of that random variable. Is it clear?
Yes, ma'am.
Okay, right. So what is the height of this curve? Very simple.
2.
It is 2. Is that right? What is the area of this curve? What should be the area if it is a PDF?
1.
It would be 1.
4 units.
It would be 1, right? What is the height of the curve? What would be the height? What do I know? The area, what is the area of the triangle?
Ma'am, half into
Half
base
of the
into
base
height.
into height.
What is my
Base into
base?
height.
Ma'am, base is
Base
4.
4.
4.
So what would
Height
be
is
the
2.
4.
Height
What would be my height?
1 by 2.
2.
1 by
Okay,
2.
is that clear?
Yes, ma'am.
Right. Now, what is the probability that she will study for more than 3 hours? It is this. Agreed. What is this chance? I know the height of the curve.
0.25. 0.25.
0.25.
5.
0.25.
Is it 0.25?
Ma'am, 0.5.
1.
0.5. Yes, what would be this?
1 by 2.
1 by 8.
1 by 2. How is it 1 by 2? This is 1 by 2. Right? So what would this be?
1 by 4
Ma'am,
into
1
1
by
by
1
4.
by
8.
4.25.
What would this area be? So what would this?
Area will be 0.25. 0.25 into 1.
What will it be? It would be 1 by 8. 1 by 4 into half times 1 into 1 by 2. Is that right? It will
1
be
by
1 by 8. Is that right?
Yes,
Now,
ma'am.
what is this probability now? That it is between 1 hour and 3 hours.
1 minus 100.
Okay, so that would be about 3 by 4 because I know that this is going to be 1 by 8, 1 by 8. Both of them, it is symmetric. So it would be 1 by 4, 1 minus 1 by 4, which is 3 by 4. Is that clear? Okay, so you should be able to understand first, verify it as a PDF. Once you verify it as a PDF, then you can apply that to answer the questions. Is this clear? Now the next question or the last distribution is what we refer to as an exponential distribution. So many a time, why do we need to understand exponential distribution? See, when you are doing an future studies about understanding what are queues. So I have people who enter a particular system and form queues. Now the number of people is discrete distribution. But the time between the arrivals, will it be discrete or will it be continuous?
Continuous.
That would be a continuous distribution. Time between arrivals is typically referred to as inter-arrival time. Okay. Similarly, when you go to a bank and you are served by any person or you go to a call center and you're served, is the time taken to serve you, would that be discrete or would that be continuous? The time taken for service.
Continuous.
Continuous.
Continuous. Will it be same or will it be variable?
Variable.
Variable.
It will be variable. Would it be deterministic or will it be a random variable?
Random variable.
It will be a random variable. So in situations where we want to model inter-arrival times and service times, just for an example, the distribution that would be very useful to us is what we refer to as a exponential distribution. Now again, what is the PDF of the exponential distribution? Again, the parameter is lambda. It is lambda e to the power of minus lambda x. I repeat, the PDF of an exponential distribution is lambda e to the power of minus lambda x if x is greater or equal to 0, 0 otherwise. And we say that x follows an exponential distribution with parameter lambda. Is this clear?
Yeah, ma'am.
Yes.
Right? Okay. So now once I know what is the parameter, the next thing is, so I have what is the distribution of the I have what is the exponential distribution. We need to know what is the shape of the distribution. For different values of lambda, you can see that lambda equal to 0.5, lambda equal to 1, and lambda equal to 2. What you can see on the screens are the graph of the PDF of the distribution. Okay. So the next important thing that we want to know is what is the CDF? What is the cumulative distribution function? Now, what would be the CDF? The way we define the CDF is f of a is nothing but 0 to a f of x dx. Would you all agree? That is how we define the cumulative distribution function. Why 0? Because my value of the random variable takes values only from 0. Is that clear? Yeah?
Yes, ma'am.
So now if I want the CDF of this distribution, I want to, what will I do? I'll do a 0 to a. I have lambda e to the power of minus lambda x dx. Again, I use integration by parts and I know that this f of a is 1 minus e to the power of lambda a. That is what I refer to as the cumulative distribution function of a exponential distribution. Is this clear?
Yes, ma'am.
Now, once I know what is the cumulative distribution, the probability density function, I want to see how the graph of the cumulative distribution works. For the uniform, we saw that it was a straight line. In terms of an exponential function, this is how the graphs would appear for different values of lambda. So you can see it is not a straight line, but it is an exponential curve. And you can see that for different values as lambda increases, how the CDF increases. Is this clear? So these are things that you might need to understand. Now, what is the expectation of an exponential distribution? Again, you can work out what is expectation of xn. I know expectation of xn is nothing but x to the power of n, f of x dx. I can do this 0 to infinity and I can use integration of parts to show that the expectation of x is 1 by lambda. Okay, and variance of x is 1 by lambda square. I think this derivation of this is in the lectures. You can go through that. Now, once I know this, I have shown this, the expectation of x is 1 by lambda and variance of x is 1 by lambda square. Now, how do we apply this? So now let's look at this example. Okay, I'll just give you 5 minutes to read and go through the example, and then we'll 3 minutes perhaps, because I think we are running out of time. Length of a phone call is an exponential. So the service time of a phone call is exponential. Parameter is lambda equal to 0.1. If someone arrives immediately ahead of you, find the probability that you'll have to wait for more than 10 minutes. First of all, what is the random variable? How would I define the random variable here? What is x here?
Waiting time.
Waiting time. Waiting time is the length, or it is the length of the call made by the person. What is it? It is length of the call, because that is what I know here, right? The length of the phone call is what I know the distribution for, right? Is it right? So when would I
Yes,
wait for
ma'am.
more than 10 minutes? If x is the length of the phone call, when will I wait for more than 10 minutes?
That the call exceeds
Greater than
X
10.
is greater than
Is that
10.
right? And I want to know what is the probability x is greater than 10. Is that clear?
Yes, ma'am.
Right.
Yes,
Now, what
ma'am.
is the parameter? What is lambda here? Now, I know that the length of a phone call in minutes is an exponential random variable with parameter 0.1. Okay. The length of the phone call is 0.1. So, what is my lambda here?
0.1.
0.1? What is
Yes,
the
ma'am.
mean? Would it be 0.1? I'm looking at what is
The
the probability that you'll have to wait for more than 10 minutes. Length of the phone call in minutes, lambda equal to 0.1. Okay. Now somebody arrives immediately ahead of you. What is the probability that you'll have to wait for more than 10 minutes? What would be your probability?
Ma'am, I think lambda will be 0.1 into 10 minutes.
Yeah, what would that be?
Or that is 1.
0.1 into 10 minutes, or what would it be? I just want you all to think about it. I think we
Ma'am,
are
1.
done.
Yeah.
Is it 0.1 into 10 minutes? What is lambda again?
Ma'am, 1.
What does lambda equal to 0.1 mean? What does lambda equal to 0.1 mean?
Length of the phone call per minute.
Is that lambda? Lambda is the parameter of the distribution. What is the distribution? What do we mean by the distribution? So what is the mean of the distribution? It's 1 by lambda, right? Okay.
Yes.
So what do I mean? How would I
Ma'am,
calculate?
expectation.
What is the expectation then?
1 by lambda.
What is 1 by lambda?
10.
10 minutes.
10.
1 by lambda is 10. Okay. Then how would you go about?
Mean length, average length of for a phone call is 10 minutes.
Is that how we do it? How would we do it? I just spend some time. This is the last problem, so I just want you to understand how we do it.
We get the fx first with this because it is more than 10 minutes, so we try to do 1 minus what would be the lesser than 10 minutes time. We find the fx.
What is fx?
F of 10 here, which would be 1 minus e to the power minus lambda into 10.
First, you find out what is your lambda. Okay, probability that you'll have to wait for more than 10 minutes. What would be the distribution of x? So what is the distribution of x? How do I define this x? That is the first thing I need to understand. Okay, the length of the call made by the person in the group, in the booth. That is what I want to know. Okay. Here I'm telling lambda equal to 0.1. Okay. So I think, so you can just put a 0.1 there and you can find out what is the probability x is greater than 10. Okay. And then you can find out what is the probability it is between 10 and 20 minutes. Is that clear? What will probability x is greater than 10 be? I know what is f of a, right? What is f of a? F of a is 1 minus f of a is, here I already have that. F of a is nothing but
1 minus e power
1
minus
minus e,
lambda.
e to the power of
minus lambda.
lambda a, right? Okay, so I just find out what is for lambda x is equal to 0.5. I'll just find out what is, so this is probability x is greater than 10 will be 1 minus e to the power of minus lambda a. Is that right? Which
Yes,
would be
ma'am.
just e to the power of minus 1. And between 10 and 20 would be a to b, that is 10 to 20 probability x is probability A is less than or equal to X is less than or equal to 20. So probability X is greater than A. I just find probability X is greater than 10, which I get e to the power of minus 1. Probability 10 is less than X is less than 20. I get it as e to the power of minus 1 minus e to the power of minus 2. Is that clear? Yeah?
Yes, ma'am.
Okay. So that is what we do. I think there is a typo in my notes. Please take care of that. Okay. When I do that. I think I've written exponential. This is going to be 1. Okay, and everything else is fine.
Ma'am, I have one question in this type of questions.
Mm.
Ma'am, whenever solving this type of questions, whenever we are given intervals of 10, 20, 30, whatever, like because it is lambda into x, we always have to multiply the parameter with the given to get the lambda parameter for that
It
particular.
depends on A is whether your length is given in minutes or in hours, and whether your question is also asked in the same units. That is the first thing that you need to understand. Okay.
Okay,
Is that
ma'am.
clear? Depending on how your parameter is given to you, and if you're asked in different units, you'll have to change the parameter accordingly. The second thing is, once you know what is the distribution, then you can answer the question based on the distribution. Of course, here there is a mistake. It is exponential 0.1, and you can answer the question that way. Is that clear?
Yes, ma'am. Got it.
That is how you do it.
Thank
So
you.
this is what was a revision which I planned to do. So it was basically we looked at review of random variables, looked at probability mass function, the expectation, the variance. Then we went on to Bernoulli, binomial, discrete uniform, binomial, hypergeometric, Poisson. Then we looked at continuous, which was uniform, triangular, and exponential. I think we have 6 more minutes. If you have any specific questions, we can look at it.
Then how we will define lambda in this question, please?
See, lambda equal to 0.1. This I said was a mistake, right? Just take lambda equal to 0.1.
No, I mean lambda is the average length
of, yeah, that's how you, 1 by lambda is the average length.
Yes, ma'am. Yes,
Okay, that is how you'll define. Is that clear?
yes.
Right? See, lambda in Poisson was the average, but for exponential, it is 1 by lambda. If you don't like lambda, take mu here, take lambda for Poisson. Okay? Any questions, clarifications? I'm sorry if I was slightly slow today or low in my voice also. I'm not feeling too well, but I hope you all had a good session.
Yes, ma'am.
Okay?
Yes, ma'am, understood.
Right.
Yes,
Thank you
ma'am.
all. Wish
It
you
was
all the
very
best.
nice, ma'am.
Wish you all the best. Thank you all. Do well. Okay. Let me stop sharing.
Thank you, ma'am.
Thank you all.
Thank
Thank
you.
you, ma'am.
Thank you all.
Thank you, ma'am.
Thank you all. All the best.
Ma'am,
Yes.
will there be questions in normal distributions, ma'am?
I'll allow Swati to answer that. Swati, do they have normal? No, right?
No, we don't have normal distribution.
Normal, yeah.
Yeah.
Okay, thank you.
Okay.
Ma'am,
Yes.
in the exponential distribution that we just now did, and similarly in the Poisson distribution, in both questions, ma'am, one thing is similar. That is, whenever the parameter is given and some distribution is asked, say 10 minutes, 20 minutes, the same unit, we always multiply to get the parameter in that particular sense, right?
Exactly, right. But Poisson is a discrete, exponential is continuous. So you need to understand when you're counting, you'll do Poisson. When you are measuring, this is the service time was what you are measuring. So that's why you are having an exponential distribution. Is it clear?
Okay, ma'am. Got it, ma'am. Thank you, ma'am.
Anything else? Any other?
Okay, thank you so much.
Okay, thank you all. All the best. Do well. Okay. Thank you.
Bye bye, ma'am.
Bye. Thank you all.
Thank you, ma'am.
Thank you. Swati, I'm leaving. Okay. Right. Thank you.
Yes, ma'am. Okay, ma'am. Thank you,
Thank
ma'am.
you.